Hello. In this video, let's start discussing about differential amplifiers. So what we'll do now is we'll first look at what do I mean by differential signaling and what are the advantages it provides. We'll then look at a very basic differential amplifier and qualitatively understand how it works. And then we'll go ahead and develop the large signal model for the operation of this simple differential amplifier. Now, what's differential signaling? So a differential circuit basically consists of two sets of input nodes and two sets of output nodes. So this is known as differential signaling, in which the input signal is applied between any two input nodes of the circuit. A differential output is when the output signal is defined again between two nodes of the same circuit. So if we've looked at it so far in the common source, common gate, etc., we had one of the terminals which was common between the input and output. So the input was applied at, say, in the common source, the input was applied at the gate pin and the output was pulled from the drain pin. It was implicitly assumed that the source pin was essentially ground and was serving as a reference. Now, in the case of differential signaling, the input is actually going to be applied across two implicit pins on the circuit. And then in the case of a differential output, we're going to talk about two explicit output pins on the circuit. Now, what is the advantage? Now, the big advantage that differential signaling comes about is if you look at these two pins, right? If they're close by, then for any environmental noise that's present in the circuit, one can assume for most part that both these pins will be affected. So therefore, if I think about a signal which I define as the differential signal between these two, then what's going to happen is that the impact of the environment or of anything that is common to these two pins is essentially going to happen on both the pins, and it's not going to infect the information if I assume that the information is stored in the difference between the two pins. So the very big advantage that differential signaling gives is it provides what is known as higher immunity to environmental noise, or in other words, it rejects the common mode noise between two pins. And because of that, you can use differential paths for sensitive signals, especially when you're using on noisy lines. So if you have a signal coming on a noisy line, having a signal coming between two lines which are close together will ensure for the most part that any noise that's coupled is going to be coupled simultaneously on both the lines, and so the difference between the lines is essentially going to be a signal which is which follows information, if you will. And finally, having a differential output allows you to have a larger voltage swing because each of these outputs can swing to the full peak to peak voltage. And so if I have a differential output, I can essentially get 2 times the peak voltage in my output swing. Now let's look at a very simple differential amplifier. A basic differential amplifier can be built off a common source amplifier. So what you see here essentially are two arms of the differential amplifier and the input that is applied between two input gates of M1 and M2. There is what is known as this current source, which is used for biasing the circuit, and this current source is known as the tail current of the circuit. And we look at how important the tail current is. We define the output as the voltage that is developed between the two drains, or between the drain of M1 and the drain of M2. So ideally we pick M1 and M2 to be as identical to each other as possible. And so what it essentially looks like is that you have two common source amplifiers, if you will, which are running in tandem, and you're applying a difference or you're applying a signal between the two common source amplifiers, and you're essentially getting the output across the two common source outputs. Now, differential amplifiers can work in two modes. One is known as the common mode and one is known as the differential mode. We'll look at that more in subsequent videos, but common mode is very simply is the mode in which both the inputs or both the input pins of the differential amplifier move in the same direction. That is, the same signal is applied to both M1 and M2. And the differential mode, which is what is normally of more importance, is when I have a signal that is falling across these two pins and I want to either amplify the signal. Now let's think about how this circuit works. Now initially when ISS is 0, both M1 and M2 are going to be in cutoff. So no current is going to flow through these two arms, no current flows in the RD, and hence both these voltages at the drains are going to float up to VDD. The differential voltage, if I define the voltage as the difference between VD1 and VD2, is essentially going to be 0. Now as I start increasing the value of ISS, what happens is the both M1 and M2 transistors move into saturation. Now if I assume that there is no differential voltage between M1 and M2, then what I can think about is that these two arms are essentially balanced, right? Because both M1 and M2 are of the same size. And so because these two arms are equivalent in most respects, this tail current essentially splits itself equally between this arm and this arm, right? And so what you have is in both these arms, you have a current of ISS by 2 that's going to flow, and hence the drains of both the transistors are going to go to a value of VDD minus ID into RD, where ID is given by half the tail current of the circuit. Now this tail current, as this ISS by 2 flows through M1 and M2, you need a overdrive voltage on M1 and M2 to support that particular current. And as you increase the input or the overdrive voltages of M1 and M2, you can support more and more tail current. And eventually, as the gate voltages of M1 and M2 increase, you tend to push M1 and M2 out of saturation into the triode region. Now, when you think about the same circuit operating in differential mode, what it means is essentially one particular transistor has a slightly different gate to source voltage than the other transistor, which therefore means that the current, instead of dividing equally across the arms, is going to divide unequally based on this difference in the voltage. So the higher the gate voltage, more current is going to flow from that branch. The sum of the currents in both the branches is the same, and that's tied because of this tail current. So therefore, when the current in one branch increases, the current in the other branch is automatically going to decrease. Which means that, for example, if I assume that the current in M1 increases, then the voltage drop across this RD increases. But because the current in M1 has increased, the current in M2 has gone down, which means that the voltage drop in RD in this arm has reduced. And so what you see here is this drain of M1 is at a lower voltage than the drain of M2, which means that there now exists a differential voltage at the output nodes between the two. And how wide is that differential voltage going to be? The differential voltage is basically going to be dictated by how different ID1 and ID2 are. And the difference between ID2 and ID1 is going to be dictated by this differential voltage that is applied between the two transistors M1 and M2. So as the differential voltages increases, you see greater separation between the two currents, and therefore you see a larger separation at the drain voltage. And this current which is flowing extra is going to have to be supported by the higher overdrive voltage because of the larger differential voltage that occurs across either M1 or M2. Now we'll see later that the gain of this particular circuit is going to be maximum when the transistors are in saturation, and we choose this common mode voltage, that is the voltage at which this ISS is going to run. We're going to choose the common mode voltage to support M1 and M2 in saturation, which means that the maximum voltage that this node can float to so as to ensure that M1 and M2 are in saturation is going to be given by V in Cm of the common mode voltage plus a threshold voltage of the NMOS transistors. Now let's develop the large signal model of this circuit. So let's establish, what do we want to do? We basically want to establish the relationship between the difference of the two currents ID1 and ID2, and how are they related to the differential voltage when it applies between the two transistors M1 and M2. So let's first assume both M1 and M2 are in saturation. We also assume that Vn1 and Vn2 are applied to the two gate terminals. Now therefore, if I look at Vn1 minus Vn2, remember that the source of both the transistors are essentially the same. So which means that Vn1 minus Vn2 is going to be equal to VGS1 minus VGS2. And so now let's assume that both transistors follow square law, in which case my VGS1 is given by 2ID1 divided by mu n C ox W by L plus Vt, because there is a current ID that flows through M1. Similarly, VGS2 is going to be defined by this ID2, and that's going to be defined by 2ID2 by mu n C ox W by L plus VTL, right? So if there is a differential voltage, there's going to be a differential current that's going to flow in this differential pair. Now, as I said earlier, we'll choose a design such that both M1 and M2 are identical to each other, which means they have the same size, they have the same VT, and therefore I can subsequently what I'm going to do is, instead of writing this big expression, I'm going to replace mu n C ox W by L by the number Kn. So now let's write V in 1 minus V in 2. We just said V in 1 minus V in 2 is nothing but VGS1 minus VGS2, which is given by square root of 2ID1 by Kn minus square root of 2ID2 by Kn. Squaring both sides, I get V in 1 minus V in 2 the whole squared is given by 2 by Kn into ID1 plus ID2 minus 4 by Kn square root of ID1 ID2. Now at all times, the sum of the two currents, that is the sum of currents ID1 and ID2, must be equal to the tail current, right? Independent of what the actual values of ID1 and ID2, ID1 and ID2 will always settle down such that the sum of the two has to be equal to the tail current. So therefore this ID1 plus ID2 can be replaced by the tail current 2 by Kn ISS minus 4 by Kn into square root of ID1 ID2. Or therefore, recollect the terms. I have half Kn V in 1 minus V into the whole squared minus ISS is equal to minus 2 times square root of ID1 and ID2. Remember, I want to establish a relationship between the difference in ID1 and ID2 versus V in 1 and V in 2. So let's square both sides again. When I square both sides, I get 1 by 4 Kn squared V in 1 minus V into the power 4 plus ISS squared minus Kn into V in 1 minus V into the whole squared times ISS is equal to 4 ID1 ID2. Now notice that 4 ID1 ID2 can be written as ID1 plus ID2 the whole squared minus ID1 minus ID2 the whole squared. A plus B the whole squared minus A minus B the whole squared. Now again, ID1 plus ID2 is ISS. So ISS squared minus ID1 minus ID2 the whole squared. So again, ISS squared on both sides cancel each other. And what I'm left with is ID1 minus ID2 the whole squared is Kn times V in 1 minus V into the whole squared into ISS minus 1/4 Kn squared into V in 1 minus V into the power 4. So again, here I have ID1 minus ID2 and I have V in 1 minus V into. So I have a differential current and a differential voltage. So I'm getting close to the answer. And so basically, if I take the square root of this equation, I get ID1 minus ID2 is equal to square root of Kn ISS into V in 1 minus V in 2 into square root of 1 minus Kn times V in 1 minus V into the whole squared by 4 ISS. So now if I define V in 1 minus V in 2 as delta V in, or the differential voltage, and if I talk about ID1 minus ID2 as differential current, then essentially I get the differential current to be square root of Kn ISS into delta V in into square root of 1 minus Kn delta V in squared by 4 ISS. So what I want to draw to your attention is that it is not a linear function of delta V in, right? Because of the square law dependence, delta V in is going to be not linearly related to delta ID. It is going to be related linearly only if delta V in is very small or for small values of differential voltages when I can treat this ratio as much larger, smaller than 1, then in that limiting case, I can treat my delta ID as delta V in, which is what we'll see in the small signal analysis of the circuit. But for large signal analysis, I don't really have a linear relationship. I have a quadratic term in the expression. So now if I plot this delta ID versus delta V in, what I get is a plot of this format. So this is delta V in from 0 towards 1, from 0 towards minus 1. And what you see is that the delta ID current goes from minus 1 to plus 1. That is, as my delta V in swings to either positive or negative, the current difference between the two branches goes to plus or minus ISS, right? So based on how much is my difference in the differential voltage, I'm going to get a difference in the ID current. Now, just like how we discussed in previous circuits, we talk about an effective transconductance. That is, when I have a differential voltage, what is the effective transconductance this circuit is going to show if I have a shorted output? So I can talk about effective transconductance as the slope of the IDV in curve, or the delta ID by delta V in curve, right? And so in the previous expression, I got an expression for delta ID versus delta V in. I take the first differential of that to establish the relationship between transconductance, the effective transconductance, again, which is not a linear expression in delta V in. In fact, you see that it has a square term with respect to delta V in. And now if I plot this, I essentially get, if I plot Gm by Gm max versus delta V in, what I see is that I see the maximum when delta V in is 0. So this circuit exhibits maximum transconductance for very small values of delta V in, and the transconductance drops down as the delta V in increases, which means that the differential gain of the circuit is going to be related to this Gm. The differential gain is maximum for very small values of delta V in, and as the values of delta V in increase, you begin to see that the effective Gm actually starts to go down, or the gain is going to be a function of this swing in delta V in, if you will. And so please keep in mind that whenever therefore we talk about differential gain, we're going to be talking at this point, or the maximum transconductance point, where delta V in is a very small quantity. And in that case, you'll see that in the small signal model, we're going to linearize the circuit around that delta V in being very small. Now, how do we talk about what this maximum input swing is? So let's assume, so when the differential amplifier is balanced, that is when delta V in is equal to 0, I have ISS flowing in both the arms of the differential amplifier. So if I talk about the overdrive voltages of M1 and M2, the overdrive voltage of M1 and M2 is given by some VOV, which is going to be equal between M1 and M2 because the same current flows in both M1 and M2. And it's given by square root of 2ID by Kn. And remember this 2 times, now ID here is half ISS. So therefore you get this as square root of ISS by Kn. Right? So that's going to be the VOV when the currents are balanced. At this time, both the VOVs are equal. Now I want to find out what is the VOV going to be so when this entire ISS has either transformed into the first branch or the second branch. That is, I want to know, suppose my ID1 goes to ISS, what happens to the value of VOV? So if I assume that all the current flows in arm 1, what I see in that case is my VOV1, instead of being ISS by Kn, becomes square root of 2 ISS by Kn, or in other words becomes square root of 2 into the VOV. So what you see is that this circuit works only when the input voltage swings between plus or minus square root of 2 VOV, where VOV is the voltage required at the time when both the arms are balanced. So this is an important term because the VOV of the initial circuit dictates how wide the input swing can be for the circuit to function as a differential amplifier. Or in other words, the differential output's voltage swing of square root of 2 into VOV is enough to swing the tail current to either one of the arms. Now remember that effective GM, however, is not going to be maximum at that point. The effective GM is going to be maximum when the two currents are balanced, right? So when delta Vn is close to zero is when the circuit is going to give you the maximum differential gain. So now with this, now that we've understood the large signal modeling, we'll now look into the small signal modeling of the circuit and look at some interesting techniques to solve circuits and to find the small signal gain of those differential amplifier circuits.